Right. I think I'm live. Hi everyone, tell me if I'm live or not. Cool. Testing. Can you hear what I'm saying? I think this is working. I think it is. But please post in chat if it is, so I know. It's working! Yay! Nice to see you, Nicholas. Thanks for letting me know. Okay. So, welcome to the MATH1081 end of term revision, where I do last term's exam. I'm basically just going to go through the whole exam, do answers, and and show you what it looks like and what you can expect. It's going to be more or less the same. Well, it's going to be the same format. Excuse me while I close the door. Excuse me, Imogen. It's good. Choking on carrot. It's going to be the same format as last term's exam. The questions will, of course, be different. And also, I've got my daughter Imogen here. She's just on the floor, making a little nest for herself. She may pop up at some stage during the during this thing. So, let me know if there's anything you want to know in chat. Other than that, let's just get to it. Okay. If you have any issues, like technical stuff during the exams, like you can just type it in here, like my internet broke, and question 3 is, stuff like that. Should I do this exam before watching this review? You don't have to. No, you don't have to. Good luck building the nest. Hey, Laura. It is a little. I mean, you can. I mean, if you want to stop watching now, and there will be a recording, of course. So you're welcome to do that. But you won't have the opportunity to ask me stuff. So there's pros and cons. Pros and cons. Let's do this. This question. Let B be bijections from the real numbers to the real numbers, and a set of all bijections from the real numbers to the real numbers. That's a lot of stuff. All possible bijections from real numbers to real numbers. There's a lot of things in there. And then we have a little thing, a little b, which is a polynomial from R to R. Show that this is a bijection from the real numbers to the real numbers. Okay. So, bijection means that it's injective and surjective. So there's a fair bit to do here. So for injective, and maybe I'll say that. Maybe I'll start my response by saying that A is both. Maybe I can make it bigger. Oh yeah, now you can see what I'm typing. A bijection is both injective and surjective. Since, okay, what's the derivative of this thing? Now notice that the derivative of this thing will be strictly positive. B prime of x equals, I'll just write 13 times 14 times x to the power 12 plus 3 times 11 times x to the squared plus 19 is strictly greater than 0. This function is strict. Hence injective. It's a strictly increasing function, therefore it's injective. It's also surjective. How do I know that it's surjective though? Well, it's a continuous function. And goes. So remember, surjective means its range is equal to its domain. So for this one, I want to say something like, well, for any element of the output. So, excuse me while I eat carrots and answer this question. This stream sponsored by delicious carrots. Get yourself some for guaranteed HD. Okay, suppose you've got any real number y, and we need to show that there's some x that maps to this thing. You don't always need to show that. You don't always need to show that f for injective f of x equals f of y implies x equals y. I mean, that's what it means, but it's much easier in this particular case to say it's a strictly increasing function and hence it's injective. And also, this is just one part of, yeah, I think, I don't really want to see any more than that. I think you particularly have trouble solve y using x. I don't really want to find what the inverse of y is. And the question doesn't require that you find what the inverse of y is. Also, the y that you don't actually have to find an inverse of y. You just need to show that some inverse exists. For that, I kind of want to use the intermediate value theorem. Yeah, I want to use the intermediate value theorem. So do we use the equation editor? I mean, you can if you want to. I mean, I'd say this is fine. That's totally readable, what I've typed there just in text, and you can use the equation editor. I don't feel that's necessary. We're not going to penalize you for, and I don't really want you getting stuck on LaTeX. You can use it if you want to. I won't stop you from beautifully rendering your math. Use it if you want to. Anyway, suppose that y is any real number. We show b of x so since now let's see. The function. I'm going to say suppose y is any fixed. So y is just some constant. You picked a y. Take a now, since the function 14x cubed plus 11x squared, and I'm going to put times this in there just because that's a good habit, plus 19 times x minus 16 minus y is, now this is a strictly increasing function. I'm going to call this thing f. F of x equals that has the property that is continuous. f of. Now f of f of 0 no, I don't think I can really do this way. Yeah, maybe I won't do it that way. I still need to use an intermediate value theorem. I've just got to find my bounds. Since b is an increasing function, there is some x such that b of x is greater than y. I think that makes sense. Y is some finite thing, and the function b just keeps getting bigger and bigger. Oh no, actually, no, we haven't shown that it's always... We have to show that it goes to infinity. Okay. Not every strictly increasing polynomial will diverge like that chi. Think of like a hyperbola, like 1 on negative x. If you look at the kind of right hand side of that, it's always increasing, but it never quite gets to 0. So you have to do a little bit more than say that it's strictly increasing. It has to be unbounded. It has to be unbounded. As x goes to infinity, the function b also goes to infinity. Similarly, hence so I don't want to say yes. So is R is all okay. Yeah, so we didn't really do that. Look, I think that's probably enough. You can get more formal with it, but that's probably enough. All right. So it's both injective and surjective. That one says it's injective. That one says it's surjective. And let's see what else they got. Oh, and maybe I'll tie a neat bow in it. Hence the polynomial. And I do want to say something about continuous functions. So the range of the functions is all real numbers. Since the function is continuous, so I've invoked some theorem that shows it's surjective, but you need to do a little bit more than show that it's strictly increasing. You need to show that it's unbounded, and therefore contains everything, and truly is actually, and more than being unbounded, it actually hits everything because it's continuous. Hence the function. Hence b is in b. Yay. Okay. Define the function f capital F by function composition. So it goes from B to B, and it's applies to a function and just invokes B on top of whatever F does. Is not continuous. Yep, that's right, Kai. A polynomial like 1 on X is not continuous. All polynomials with, thank you, Kai, with positive powers are elementary functions and are therefore continuous. Thank you, Kai, keeping me honest. Prove that F is a bijection. Okay, so let's just consider what this one actually means. That function, we've got function composition here, and so for every bijection. Okay, so let's do this in two parts. This one's a bit freaky, and for this one, now I want to be using the definition of injective. Suppose prove suppose f of f equals f of g. Then, well, what do I know? Then I will format this one in LaTeX. I don't really have an O symbol. B circ f equals B circ G. Because it's function composition. Since B is a bijection, the function B, the inverse so now I'll just do that again, and so B inverse circ F B circ F equals, just copy that. G. And that one's going to just be equal to G, and that one's just going to be equal to F. And maybe I'll center it so it looks pretty. Full stop. Yay. Hence, F is injective. Good. And maybe I don't even need. Yeah, I'll leave the prove injective there because it just helps people to see what I'm up to. Prove sur. Suppose. Okay, now to prove surjective means that for every bijection there's something that maps to it. Suppose y. Suppose I'll call it G. G. G in B. Suppose G is in B. Would you get penalized if you wrote BOG? BOG. No, I just think it looks prettier. And it doesn't. Well, I just think it looks prettier to write of with the circle. Oh, no. I'm just being pedantic. Prove surjective. Suppose you've got some function in here. Since now to prove that it's actually in the in the range of the function f, we need to find something that maps to it. Since well now, bog champ. Okay, so what's going to map to G? I actually want to find something that maps to G now. Since now the only thing that I can think of that's going to map to G is going to be f applied to B inverse circ G.
I want us to do ABC.
Because that's going to be equal to B circ B.
Daddy, can I watch this? Daddy, can I watch this? Daddy, can I watch this? Daddy,
Yes.
can I watch this?
Sure. But I need to show that B inverse of G is actually a is also in B. That's what I want to do, but I need to do that. To pull that kind of stunt, I need to say, yeah, I need, since B okay, so that's the structure of what I want. Since okay, so since how do I know that B inverse of G is in this thing? Well, B is a bijection, therefore B inverse is also in B, and by function composition, B inverse a composition of bijections is bijective. Since because B inverse so B inverse is in B, and maybe some words here, since B is a hence F is surjective. Okay, so in this case we did actually find what the inverse of G was, and it was B inverse of G, because all you're doing is just slapping a B on top of that. Okay. End of question. All right, next question. In the first part, we're interested in the congruence 30x equivalent to 18,183. Some dude claims the first step to solving this congruence is to apply extended Euclidean algorithm and show all lines of work that they would have to write down when applying the extended Euclidean algorithm this way. Sure. Okay. So remember, what we're solve 30x plus. Yeah, I'll do it as plus 80. 83y equals 18. So 83. 83 is equal to something times 30. Well, that's going to be 32 times 30 plus 27. Then everything goes down and to the left. 30 is equal to 1 times 27 plus 3. 27 is equal to 9 times 3 plus 0. Bum, bum, bum. Hence, well, 3 is equal to 30 minus 27. And 3, so if I replace the 27 here, that's 30 minus 83 minus 2 times 30, which is equal to, I've got 3 times 30 minus 83, which, does that make sense? That's not right, because that's 90 minus 83, which is 7. 23, that's 23, that's 23, ugh, yuck, 23, 7, 23 is 3 times 7 plus 2, 7 is 3 times 2 plus 1, okay, hence the GCD is 1, okay, let's try that again. Hence 1 is equal to 7 minus 3 times 2. Are we allowed to use Maple to check the calculations as a result? Yes, you are. You're allowed to use Python or what have you. The questions have been... Don't feel like it's necessary to teach yourself Maple to do these questions. If you've got your pocket calculator, that's fine. If you've got Python, that's fine. If you've got Wolfram Alpha, that's less fine because it'll... Yeah, let's not go there. If you've got your genius mate next to you who knows all the answers, no. But if you've got a calculator of some kind that can check your answers, totally fine. And if it's something like Maple, okay. But don't feel like you need to learn programming to be able to do the exam. The exam has been written for people without calculators. Much like I haven't had to use a calculator yet to answer these things. And it would have been, yeah, why can't I scroll down here? No, there we go. It's all there, I just couldn't see it. Okay. Okay, so 7 minus 3 times 23 minus 3 times 7, which is equal, oh, maybe I can clean that up a bit before I go to the next line, which is, how many 7s have I got? 4 of them. 4 times 7 minus... No, that's 9 times 7. So that's 10 7s. That's 3 times 23. And now I can get rid of the 7. That's 10 times 30 minus 23 minus 3 times 23. Which is equal to 10 times 30 minus, how many 23s have I got? I've got negative 13 of them. And now I can get rid of the 23. So this is 10 times 30 minus 13 times 83 minus 2 times 30, which is 10 times 30 plus 26, so it's 36. 30 minus 13 times 83. And at this point, I am going to get my pocket calculator. And just make sure that adds up. 36 times 30 minus 13 times 83 it equals 1. There we go. Alright, in order to solve the equation, Harrison should multiply both sides by which numbers? Okay, so I'm trying to find the inverse of, it's not exactly the best worded question, but in order to have this expression as x equals something, you multiply by the inverse of 30. Which of these numbers is the inverse of 30 mod 83? Well, it's right here, 36. Oh, in mod 83 land is that? Oh, here we go, 36. Now, is 36 equal to something mod? I'm just concerned because they've got select all values that apply. In mod 83 land, 36 minus 83 is negative 47. That's also an inverse. Well, they're the same number in mod 36 land. Yep. 1 over 30. Well, yep, negative 47 is the same as 36 in mod 30. 1 over 30? I kind of agree with that and I kind of don't. You can't multiply by 1 over 30. 1 over 30 is not a... Oh, this is me just being Babylonian though. Should I click 1 over 30? I mean, theoretically, that's both. Why do we need to write both these numbers on both sides? You need to multiply both of these numbers on both sides by 1/30, which is the same as 36, which is the same as mod negative 47 with your mod 83 goggles on. So you put on your mod 83 goggles. Oh. Yeah, I don't like the idea of multiplying by 1 over 30, although they're probably trying to give me a clue. I think it does want you to click 1 over 30, and as a matter of principle, I'm going to click it because the person who wrote this exam probably wants me to click it, and even though I don't like it, I can check answers. Hey, how did I do? Oh, partially correct. Or maybe 1 over 30 is not okay then. How did I do now? Hey, there we go. The answers say no to 1 over 30. Okay, good. Yeah, 1 over 30 is a bit misleading. Part of me feels like that should be correct, and part of me feels like that's not legit. You can't multiply by 1 over 30. Anyway. Harrison found a solution x to the congruence where x is an integer between negative 747 and negative 664. Okay. What x could they have found? Well, I'll switch over to x equals 18 mod 83. Let's switch over to here. So solve x so 36 and this is just equal to x because 36 times 30 is just going to equal 1. Maybe I'll write it down here. So that's just going to be equal to 1 on the left hand, or x on the left hand side. 36 times 18. 36 times 18 is equal to that. Is equal to 648. It's equal to 648 mod 83. So now I need to keep subtracting value, so which means x is equal to 648 648 plus 83k, where k is just some integer. And what if I let k equal to, I'm just going to try a few values of k here to get it k in the right range. If I try 648 minus 20 times 83, no, that's too big. 648 minus 15 times 83, that's too small. 648 minus 17 times 83. Ooh. So if k equals negative 17, then x equals negative 763. So now going back to my question. Okay. Too big. I need to do negative 16. Sorry. 648 minus 16 times 83 equals 680. Negative 680. Negative 680, which is what I get when I choose k equal to negative 16, and I think that's correct too. Let me just see how I did. Yay! Oh, Harrison just keeps going. Sorry, just... Yeah, okay. Okay, Harrison next considers a more general congruence. AX equals 3 mod 72 for integers in that range. Okay. For which values of A will there be no solution? Okay. So now I need to think about 34, 35, 36, 37, 38, 39. Ugh. Okay. Get my piece of paper back. Okay. And let me just need that, and I need that in the background. Okay. So alpha x equals or equivalent to 3 in mod 72, where alpha equals, well, 34. Alpha equals 35. I need to consider each of these. Alpha equals 39. Okay. All right. Now, 72, that's divisible by 6. So which of these things are... This one here is going to be fine. This one's coprime. 35. So alpha inverse exists since GCD of 35 of alpha and 72 is equal to 1. So that one, this one's going to be fine. There's going to be an inverse to that. This one's prime as well, so this one's going to be absolutely fine. That's not prime. Yeah. So these two, these ones here, are going to be absolutely fine. These ones.
Daddy, can I go on to Netflix?
No, you can't. You can't go onto Netflix. Sorry, Imogen. Okay. This one is not going to be fine. 34 is not going to be fine at all, since there are. Well, think about it. This alpha x will be a multiple of 2. This thing is a multiple of 2. You'll never get multiples of 2 adding up to 3. So the fact that alpha and 72 share a common factor, but that's not shared with 3 means that that's not going to fly. Similarly, that's not going to fly. This one will fly. This one will fly. It's a bit more subtle though. So these are no solutions. No solution. Now these ones have multiple solutions because you've got they're both multiples of 3, and everything is divisible by 3. So this one would reduce to, in this case, that would just reduce to what would that be? 6x equals 1 mod 12. So that's got no solutions. So there's another no solutions for us. Boom, boom, boom. Because you can't solve that. And this one down here, let's investigate that. This one would be, well, that would be 13. X equivalent to 1 mod 12, just dividing everything by 3. And
Daddy?
Yes, Imogen.
Can I watch that?
Sure.
Is it that bad?
And that's fine. In fact, x is just going to be equal to 1. Yeah. Okay. So I think I know which way to go. 39 is okay, but there'll be multiple solutions. Given the solutions, x equals 1 mod 12, and 37 and 35 have unique solutions. Everything else has no solutions. So let me type that in, see what happens. For which values of a will there be no solutions? Just get my, get over there. Swap back to this. Is this basically a question? Yes, it is, Kai. Basically, you are just comparing those things. Okay. So, for which values of a will there be no solutions? Come back here. So, I'm thinking 34, 36, and 38. For which values of a will there be exactly one solution? 172. That's going to be 35 and 37. From which values of a will there be more than one solution? 172. That's 39. All right. How did we go? Come on, I don't want to do this again. Oh, look at that. Nailed it. Describe a general rule for determining how many solutions where there will be mod m. Okay, so this is pretty much what we've done in lecture notes. So if GCD of A and B equals 1, then there are unique solutions. Else, otherwise, if GCD of A and B, so A and M, that's A and M, not A and B, A and M. A and M. Yeah, thank you. I got there too, Kai. Otherwise, if GCD is if that's D, this if divides B, there are GCD of AM solutions, whatever the GCD was. Else. You know what? I don't need the otherwise there. If GCD AM does not divide B, then there are 0. You know, I don't even need that first line because that's covered. When the GCD is 1, then it'll divide 1 divides B, whatever B is, and there'll be 1 solutions. And more generally, if it's the GCD of A and M is some other number, or just call it D, then there'll be D solutions, and that covers the previous case. Whew! Oh man, lengthy question. Okay, next one. Isn't one already covered in? Yeah, you're absolutely right. Rose's favorite partial order on the set appears in the Hasse diagram given below. It kind of looks like a diamond, or yeah. Cool. I need to make this smaller so I can get it all on the screen. And the edges in this graph are there. Sorry, could you explain the criteria for choosing these numbers? B. That is the criteria. Sorry, I'll just bring that back. In the previous question. That's the criteria, right there. That's how I'm choosing. I'm looking at the GCD of A and M and comparing it to B and seeing whether or not it's going to divide. And I'm chopping off the case, the particular case where the GCD and A and M is 1, because that's going to have one solution. And the case where GCD of A and M is not 1 but still divides B, that's going to give me multiple solutions. And the third case where GCD and A and M is not 1 and it doesn't divide B, that gives me yet another suite of solutions. So your answer is right there. It might be a bit concise, but that's more or less it. Alright, here's my set, and their elements are related. Tick all statements that are true. Is G related to D, or is G less than D? Nope, G's all the way out there. D's down there. That's false. Is D related to D? Yes it is. Remember, it's a Hasse diagram. It's a partial ordering, which means it's reflexive and everything is related to itself. Is D less than G? There's G, there's D, D is less. Find all the maximal elements of S. Let's look for the maximal elements. I'll remind you, maximal elements are everything that's as big as, with nothing above it. Chat, do tell me the maximal elements of this set. Anyone? Should I just keep drinking? Oh, G and H. One more, guy. One more. And C. Yep. G, H, and C are the maximal elements. So C, G, and H. Find or explain why they do not exist. The least upper bound of... Yep, I like that people got C. The least upper bound of D and E, and the greatest lower bound of D and E, G and D. So D and E. Let's look at D and E. D and E have G above them. So the least upper bound. So of of D and E So when you're talking about upper bounds of D and E, you cut out everything that's not above D and E. So G is the only thing that's above D and E. It gives you this kind of sub-Hasse diagram. And you can talk about the least element of that sub-Hasse diagram. And this would be a least, that would just be G. The greatest lower bound of G and D, here's G and here's D. You just look at the sub-Hasse diagram of everything that's both below G and below D, and there's a great, and that would be the whole branch D, B, and A. Well, we've got a kind of similar situation here. The least upper bound in this case would be D, because of all the upper bounds, lower bounds, you've got D, you've got B, and you've got A. So just that branch, and D is the greatest of them. The lower bounds of D and G are D, B, and A. Is D, and this is the greatest bound. Cool. Alright. Do I click? How did I do here? Yay, yay. This, I mean, that gets read by a human, so don't get grades on that. You won't get a "How did I do" button on your exam, by the way. You don't get that. For a sequence, we say that it is eventually even if there exists an n, which is an integer. For all integers greater than n is even. Or for all n greater than, doesn't specify n is an integer, but I'm assuming it is. Write symbolically the statement A is not eventually even, simplifying your answer, so the negation symbols. And there's a blue, apparently there's a blue help box, there you go, on how to do your stuff. Okay, so the negation of this thing is, behold, equation editor. Now remember, when you're negating a statement, the exists become for all, so for all n in MATH1081 exists n greater than n, a n is, I'll just finish the is odd. Yeah. So swapping the exists, just toggling from exists to for alls, and then you negate the final statement. So not even is the same as odd. Prove that this sequence is not eventually even. So eventually even meaning that eventually there'll be something that's odd. And this one is not eventually even. How do I know that? Okay, so for any, I'll just have to look up here. Suppose you've got any capital N. So suppose for any venture N, I need to find something bigger than capital N. That is that gives me an even number here. So this needs to be odd. This needs to be odd. Oh, absolutely. That's what we're going to do. I'm just going to find the n that's big enough that makes this odd. So what's going to happen here? If I add an, let me just think what happens here. N's going to be really big, and it's going to be even. Well, this, Well, no, it'll be even for big N because this floor function here. Oh, hang on. I see what you're saying. So 28N is just going to be 28 plus. Yeah, so eventually odd means I need to find some number that produces an odd AN, and this is going to be 45 plus 28 plus something divided by a really big number, which is going to be, and N is they're all going to be odd for big enough N. So for big enough N, let's write this down. I'm gonna write this as N equals 45 plus 28 plus 99. How do I write floor again? I need to check. Now I need to check the instructions. Floor. There you go. That's nice. I didn't know that. Floor 99 trash 905 N. Floor. Is that? Okay, sure. I'll just leave it like that then. Floor that. I mean, there are fancy ways to render it, but they say I can do that. I can do that. And for any integer n, I'll say positive. Let the n equal that. Then an is equal to that equals 45 plus 28 is 73 plus floor frac 995 plus n. And that's going to be equal to 73. Because 995 over something bigger than 995 is going to be less than 1, and the floor of that will be hang on, do that. Is n starting from 1? Yes, it is. Nice. Okay. And maybe I'll say it's max. Because n could be, technically n could be negative, although I don't think they intend it to be negative. And I'm going to make it a 996 just in case n is 0. And 996, whichever's biggest. And that's going to be a 996. Got too many brackets there. Ding. Done. Yes, it is. 47. Thank you. 47. Thank you. 475 plus 28 is going to be 503. Cool. So in fact, the whole sequence is just 503s all the way. Once you make n big enough, it's just always going to be 503. Cool. Next question. You're so lost right now. Oh no. Well, maybe I can help with, maybe truth tables will help. Truth tables are nice. You just this one's an easy one. You just have to fill out the truth table, P or not Q, and that's going to be P. Not Q is true, so this is true. P not, that's going to be true. False and not, false and false is false. False or false is false in this one. False. That's going to be false. Yeah, the sequence proof is easy once you realize it all just converges. All the numbers become 503 after a while. True, 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 and true. So I did the first statement, the second statement being P or Q, or not Q or R. So I'll just go through and I can do all the things in, that's going to be true. R is false, so that's that's false, because false or false or false. True, and then down here all the, yeah, that's just going to be true, 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 true. And then the final statement is first one implies second one, so that's true, true, true. False implies true is true. True implies true is true. True implies true. True implies true. True implies true. Yay! How did I go? I did good. Hooray! Joseph is trying to learn about a sequence defined using the function f. And they have so far defined the following recurrence relation. Oh my goodness. Solve the initial value problem into your solution in Maple syntax. Alright. Now I need to go and solve a problem. Okay, maybe I can explain it, and then as I'm explaining it I can figure out what it is. Okay. Why did false imply true? False implies everything. It's like me saying that, you know, if you give me $100, if you give me $100, then I'll give you a washing machine. Now it's still a valid deal, even in those cases where you don't give me $100. In fact, in that case, this is trivially true. You can only catch me out if you give me the $100 and I fail to deliver the washing machine. That's the only case where your deal, the implication is said to be false. It's when you give me the $100 and then I don't give you the washing machine. Or true implies false is the only case where it's broken. All right, let's do this. Say x. Yeah, I'm just going to say x. I can say lambda. Lambda. You know what? I'll even render it beautifully. So lambda minus 3. Five plus 6 equals 0. Is it minus 5? Yep. Hence the homogeneous solution. Well, no. So lambda is 2 or 3. Is the solving the initial value problem the same thing as solving the homogeneous equations? They're not exactly the same. There is overlap between them. So initial value problems just means you are given these things. The A and B you won't always get given initial conditions. You will always solve the homogeneous equation. That's always going to be a thing you do. Sometimes you will get given initial conditions, and it becomes an initial. In which case, it becomes an initial conditions problem. Okay, the particular form P of n. Now, I would really like to choose 3 to the n, but I can't because that's part of a homogeneous solution. So I'll choose c times n times 3 to the power n. So if I sub this in, then I get c times n. So this is going to be p. This means pn minus 5 p times p n minus 1, 6 times p n minus 2, which is, and then this whole thing has to be equal to 3 to the n, but I'll take out the common factor of, I'll write it as c times n times 3 to the power n minus 5 times c times n minus 1 times 3 to the n minus 1 plus 6 times c times n minus 2 times 3 to the power n minus 2 equals 3 to the n. And I can simplify that a bit and find out, it's one equation with one unknown. I can take out the common factor of, you know what, I can divide everything by 3 to the n minus 2, and I'll take a common factor of c out the front. C times, that's 9n minus, that's going to be 15 times n minus 1, and that's going to be 6 times n minus 2, and that's going to be equal to 9, close brackets. It does take longer typing out, and the n's cancel because I got 9 minus 15 plus 6, which is nothing, and I get left with c times, well, 15 minus 12 is 3, equals 9, so c equals 9, 3. Oh, okay, so now I've typed out my solution. I can say what f of n is. Oh, no, sub in initial conditions. What my initial conditions? F of 0 is 2. So f of n, let's just get what we've got so far. It's equal to h of n plus p of n, which is equal to, well, h of n was that stuff. plus my
hair.
3 times n times 3 to the power n. Now we can use the initial conditions to find a and b. F of 0 equals minus 2, which is equal to a times, well, that times to the power 0 plus b, a plus b. F of 1 equals, what was f of 1 supposed to be? And that's a minus 2. And f of 1 is minus 7. No, there you go. Minus 7, and that's equal to 2 times a plus 3 times b plus 3 times 3, which is 9. Okay, so presumably we can solve this. My brain's starting to abandon me at this stage. So a plus b is minus 2. I can simplify this to, so minus 15 is minus 16 is equal to 2a times a plus 3 times b. Can we figure this out? Probably. I'm just going to write something down quickly. So minus 16 is twice minus 2 times b plus 3b, so that's minus 16 is minus 4 minus 2b plus 3b, which means they cancel, just leaving a b, and 4 to both sides. B is minus 12. And that means a equals 10. Whew. Okay, so now I can fill out the thing. 10. Oh, go away. 10, so that's 10 times 2 to the power n plus minus 12 times, no, that's 3 to the n. A was the code. No, a, that's right. A plus 12 minus 12 times 3 to the power n plus 3 times n times 3 to the power n. Oh, jeez. I didn't even... No! Oh. What? Solve the initial value problem.
Is it swimming lessons time?
No, it's not swimming lessons time. What have I done here? Oh dear. But that's, I mean, that doesn't... The question needs to be typed something like this. The question needed to be typed that way? What? Oh, it needs to be typed. Does it really need to be typed that way? Okay. Alright, let me type it that way then. Okay, so plus negative, like that. Why does it not like my answer? Did I get the coefficients wrong? I don't see what... Unless I've messed up somewhere in my initial value problems. Minus 15. Is that not what I had? What? They want that. So you're saying it's minus, they want minus 15 times 3 to the n. That can't possibly be the answer. 3n plus 3, that's exactly the same as what I wrote. Plus 3 times 3 to the n. Oh my god. Why would you... That's not right. That's the same as my answer. That is my answer. That's... Okay. I don't know why that is.
The investigators.
What did you write there? Good work.
The investigators. The investigators.
I don't think it's got it on here.
It's on ABC Me.
Is this ABC Me? No, this is I. If I go here, ABC Me. I don't think it's on it, darling.
Okay.
Sorry, kiddo. Okay. Try. I think there's some difficulty. So B is minus 6. Oh, is it 2B is 12? Really? I don't think it, Amy, I don't think it needs to be, it shouldn't need to be that way. I think there's something's not right with this that makes me feel like
This.
Yeah, it shouldn't need to be that way, because that's the same thing. I'd say that's a question design problem because it should accept equivalent answers. Like I wonder what happens if I put that term at the end. Like this should be the same, but I'm not even convinced that that's going to work. Is that correct? Okay, that one's correct. At least that one's correct, but it should accept, different arithmetic. But certainly that's the same as that. But it doesn't like that. What if I say, ooh, plus 0? Do you like it now? I don't know. All right. Annoying. I don't know why it doesn't like that. Anyway. Next question. For the answers below, using C and P and using stars for multiplication. So you've got 26 uppercase letters in the English alphabet. How many 25-letter words contain the subverb hammer time twice? An example of such a word would be mo hammer time, p hammer time, zzz. Okay. So you've got how many letters in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So treat hammer time as a special.
Daddy,
Yep.
can I watch that?
Yes, you can.
I just have a hug. What time is it? Swimming lessons time?
Not yet. Do you want some food?
Yeah.
Okay. Do you want some water?
Yes, please.
There you
Because I'm gonna have this kitten.
go. Okay. Okay. Behold my excellent parenting. Just lots of come to work with Daddy and get lots of iPad time. So we got 10 characters in hammer time. 1, 2, 3, 4. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So treat that as a special character. How many 25-letter words contain the word hammer time twice? Well, you can choose... Treat hammer time as like a special letter. Let's call it K. Well, let's call it Aleph. First non-uppercase letter that comes to mind. Let's call it Aleph. So hammer time is a special character, and it has to occur twice in our word. So we can choose 2 out of essentially, well, there's 5, 1, 2, 3, 4, 5, 6, 7. There's 7 places in our word, because the hammer time ones are special ones. So from 7, I'm going to choose 2 places for the word, hammer time. And then the rest of it is just 26 uppercase letters. 26 to the power 5. So choosing my 2 places for the hammer time word, and then the rest. Sounds good? Sounds good. How many 25-letter words do not contain the subverb hammer time at all?
Another cucumber.
Don't eat the marble.
Okay.
Okay, so how many words do not contain the subword hammer time at all? Well, how many contain them? So this is going to be an inclusion-exclusion thing. How many words contain hammer time at least once? How many contain it twice? So if I've got the 25, let's talk about the ones that have hammer time at least once. So just hammer time equals, well, again, I can do my special. I've got C. Well, I can choose. How many places can I choose this? It's a special 10-character word, so I can choose 16 possible locations. Yeah, so that's words containing hammer time at least once. Maybe I'll write it that way. At least once equals, well, I've got 16 being the number of places I can put my aleph, then 26 to the power 15. Now, it may happen that in those remaining 15 characters, I've got another hammer time. So I need to, number, the number of words that contain hammer time is, well, it's going to be whatever I had here minus the number of words, because that's going to do a lot of double counting, and then minus my answer to part A, 7 to the power times 26 to the power 5. And the number of words that do not contain hammer time is, well, it's going to be 26 to the power, 25 to the power 26 minus all the ones that we just had there. And I'm just going to copy that and paste it in here and cross my fingers. How did I do? Oh. Is it 15? Hang on, let me think about this. I've got 25 letters. So I've got 1, 2, 12, 13, 14, 15, 16. Yeah, 16 positions where I can put hammer time once. Don't feel like the rest of the word that way. Why is it minus? I thought it was a plus. No, because this number of words that contain it at least once. So think about it as the first means you can have. So I can have a hammer time the first time. Well, it's going to count a word like this twice. Once where you've got the hammer. Once where the hammer time gets inserted here, and a second time where the hammer time gets inserted here. So this counts all the doubles. It double counts all the times where hammer time occurs twice. So I have to remove one of those copies, which I do with my answer to part A. I think I've got some kind of formatting error here. Do not contain this hub word hammer time at all. 25 to the power 26. Oh. Oh no, that's right. At least once is 15. Sixteen positions. Okay, that's very big. It's because my at least once is wrong, possibly. But how is my at least once wrong? Because I've just got one hammer time symbol. When you do 16, you're making it so that there is no other hammer time. No, I'm using. Why is it 20? Oh. Yeah, that's the problem there. It's 26 to the power 25. There you go. Damn dyslexia. 6 to the power 25. Because there's 26 letters. Yeah, okay. How did I do now? Hey, thank you. Big HD for Joel. Yeah, it's the right method, but just 26 and 25 look similar to my brain. Okay. There we go. How are we going here? Alright, I can do this. 108 student who has enjoyed studying relations and combinatorics. They want to see if they can bring to light about what they can bring to light about the number of relations between general sets. Starts by setting V to be a non-empty set with L elements. How many binary relations are there from V to V? Explain your answer. How many binary relations are there from V to V? So relation doesn't have a lot of... Okay, so remember, a binary relation doesn't have the full structure of a function. Binary relation is any subset of the Cartesian. It has L squared elements. Okay, fair enough. Binary relations are just any subset of the Cartesian product is as a binary relation. How many reflexive relations are there from V to V? Ooh, that's tasty. How many of these are reflexive? So that means you've got at least L being at 1 related to 1, 2 related to 2, 3 related to 3, and so on. So your relations have at least those L elements in it, and then potentially a bunch of other stuff. So you're going to have there, so a reflexive relation will always contain those, which means there are so you've always got, and there are L such elements. There are L such which is L. It's L, right? Yep. There are such elements in the relation. So there are L squared possible relations, which means for every element you've got an option of choosing the remaining L minus 1. Yeah, so it's L minus 1 all squared. Because you can only choose. So you look at your relation. You can only for every element you have to choose its corresponding element in the Cartesian product, and then you have the option of choosing L minus 1 other things, and you do that for every L. So it's L minus 1 all squared. How many anti-symmetric relations are there from V to V? Now, anti-symmetric. Let's write down what it means to be anti-symmetric. If a anti-symmetric when now if A is related to B, A I'll say that in terms of if a relation is anti-symmetric if A and B if A, B and BA are in the relation, then A and B are the same. So there's only one way for A to be related to B and B to be related to A, and that's if they are the same thing. It allows the relation to be anti-symmetric. I mean, reflexive. So, can you explain the reflexive one again? maybe I'll draw a picture. That might be the easiest thing to do. Okay, let's go back to here. So you've got some set. You've got some set V. It's got some elements in it. And here's some other set V. It's the same set. Okay. So there's L. This is the set V. Here it is again. And we're going to define a relation, which means just pairs from one to the other, and I'll indicate them with lines like this. Okay. And this might be the element A, and this might be the element B, and it's going from the left to the right, like so. And this arrow means that A, B is in V cross V. I'm just using the arrow to show you which bits are in the relation. Okay. Now reflexive means that everything is related to itself, which means if we're assuming the relation is reflexive, then that element A must map to itself over here. So A maps to A because it's reflexive, but A might also map elsewhere. We have L-1 possible choices. This is not a function. You're allowed to let A be related to itself, and then something else as well. You're allowed to let A be equal to loads of other stuff, but you have to choose this top one. You have to choose A to be related to A, but it might also be related to other stuff, B, C, D. You don't know. You don't care. It's allowed to be related to all those things. So A is related to A, and then there's L-1 additional choices for what else A can be related to. And then for the next element down, you choose another L-1 choices for this. You have to, your hand is forced though, you have to choose this next element to be related to the corresponding choice over here, but you have L-1 other choices to make. Similarly, this one has to be related to here, but you have L-1 other choices to make. And so you've got L-1 choices to make L-1 times, meaning L-1 all squared. Possible relations. Does that make sense? It's not a function. It's not a function, so you're not obliged to turn them off or on. You've got 2, you think it's 2 to the L-1? Is it 2 to the L-1? Ah, no, I agree with you. It is 2 to the L. Hang on. So yeah, it's L-1. Yeah, okay, I agree. You're right. So L-1 choices, and I can turn each of those lines off or on. Okay, and I get that L-1 times. Yep, L times 2 to the L-1. Yep. Okay, I'm with you. Yeah, so you're turning off or on all the ordered. You are turning off or on all the ordered pairs, except you always have to turn AA on. AA is always on. So let me. There are L things to choose from, and each of them has 2 to the
Daddy.
L.
Daddy.
-1.
Daddy, can I watch this? Can I watch that?
Yep. Yep. Which means I have to so a binary relation. The element v cross v. There are 2 to the elements of that, but I actually want to see. What I need is the power set of that, because I want any subset of v cross v. So it's going to be is any subset of the Cartesian product. So v cross v has 2 to the L elements. There are 2 to the power L squared elements, because it's the number of subsets of that relation that I have. So there are since what we're actually talking about is any subset of the Cartesian product, and the subset that so we're looking at the power set of v cross v. Okay. How many antisymmetrics are there? Antisymmetric relations are there? Oh, you can't see what I'm typing. Of course you can't, because I'm still on the other screen. Oh, sorry, I was over here, and I changed my answer to part A. Even though it still said that a binary relation is any subset of the Cartesian product, but there are 2 L squared elements of these, but I'm talking about the subsets. So how many subsets are there? Well, that's really the power set of v cross v, and there are 2 to the L squared elements in that. Okay. How many of them are antisymmetric? So if you have A is related to B and B is related to A, then both A and then A is equal to B. So you're allowed so A and B are allowed to be related to one another. So let's think about this for a moment. I'll bring back my piece of paper. So we've got a set, and it's got a bunch of elements in it. So here's my elements. Now I'm allowed to have these things. They're permitted, although it's not necessarily reflexive. So maybe it's related to itself, maybe it's not. But if I've got one element related to another, if I've got that, then I'm not allowed to have that. That's forbidden, basically. When these two dots are distinct. So I've got distinct dots here. If I choose one of those things, I'm not allowed to choose the reverse. So coming back to our coming back to the style of diagram we had before, if I've got my dots, I've got L dots here. Like so. I've got L elements and L elements over here. Now it doesn't have to be reflexive. If every time I choose one of these things, I'm not allowed to choose the reverse. So if I choose that one, so here's A, here's B, I'm not allowed to choose B, A. Oh, yeah, sorry, B to A. That's forbidden. So A will have L options, but B will have L minus 1 options. Well, it really depends on how many things map into B. So if A's got, if there's lots of things mapping into A, if there's lots of different things mapping into B, then B can't map back to them. So B's options are restricted by however many things are mapping into it. I'm wondering if it's easier to look at the ones that are symmetric here. So what I'm thinking is look at all the cases where the maps are symmetric. And how many are we going to have? Well, if A maps to A, then A maps to A, that's fine. If A maps to B, then B maps to A. So look at all the cases where it's symmetric and then remove them. That's what I'm thinking. And I'll have to carefully deal with the the ones that are only reflexive, because they might be tricky. For every n choose 2, we can either choose A and B or B, A, or none of them, right? Oh, yeah, that's a nice way of thinking about it. So there's the possible arrows here. All the different arrows we could choose between these two things, kind of like a bipartite graph. There are potentially, so there's potentially an arrow going from A to B. There's potentially an arrow going from B to B. There's potentially an arrow going from B to A. There's potentially an arrow going from A to A. Actually, it only applies to ones where they're different. So there's L squared possible arrows. There's L squared possible arrows, but let's think about the ones coming out of A. So and the ones that are It's a tricky one. Ooh. Ooh. Okay. Okay. So there's okay. I keep trying to write on my mouse pad. So So how many relations are not antisymmetric? So A is, if A, there's going to be one where A relates to B and B relates to A. There's going to be, well, there's a whole bunch with that. But then I have to do inclusion exclusion. I don't really want to do that. There will be some hard questions in the exam. But a lot of easy questions. I might leave this one for now. Maybe I'll leave this one for the end and post a solution up on Moodle, because it's not coming to me right now and I've got the rest of the exam to do. And I don't want to get stuck on one question. So, TBA. BA. Consider the weighted graph below. What is the minimal spanning tree? Minimal spanning tree. Okay. Minimal spanning tree. That one I can do. Oh, you can't see the question. Okay. Thank you. So here we're just going to do a minimal spanning tree question. There's that thing. Okay, what is the weight of my minimal spanning tree? Oh, you can't see what I'm doing again. So I've just copied it over here so I can draw on it. I'm going to go through and select all the edges that are small and don't small, starting from the smallest weight, provided they don't make a loop. So there's a 1. Choose a different color. 1. I'm going to select that. Looking for 1s. Oh, that's my only one. So that's my only one. Okay, I'm selecting it. Next I go through all the 2s. There's a 2. There's a 2. There's a 2. Where's there any other 2s? No, I think that's all the 2s. Then I go through all the 3s. There's a 3. There's a 3. That's all the 3's. And then I go through all the 4's. There's a 4. I don't need this 4. That's forbidden. I don't need that 4. That's forbidden. I don't need that one. That's forbidden. I do need this one. Any more 4's? Nope. A 5. No, I need it. There's a 6. Oh, there's a 6 as well. And that's it. And so the weight of my minimal spanning tree is, according to this, 1 plus 6 plus 6 plus 6 plus 2 plus 2 plus 3 plus 4 plus 3 plus 1 plus 2 plus 4. 36. Yay. Easy question. Easy question. Next one. Jackson and their friends have been part of a very close friend group, but recently some other people have had a falling out. Jackson realizes that their friendships were represented as a graph. It would be a complete graph with a single edge removed. Let n be greater than or equal to 3, and let Gn be the complete graph with one of its edges removed. For which values of n does it have an Euler path? Now, Euler path means exactly 2 vertices of odd degree. So, you've always got n minus 1 edges. So in this case, you've got k equals 3. K equals 3. That's a triangle, and you remove one of the edges, and you've got 2 edges of degree 1. That's fine. Here, everything has degree 3, except for 2 of them that have degree 2. So that's fine, because you've got 2 odd, 2 even. Here, everything has degree 4. There's 5 vertices. Everything has degree 4, except for 2 of them which have degree 3. That's fine. Here, everything has degree 5, except for 2 of them which have degree 4. That's not okay. You can only have 2 of degree 3, 2 of odd degree. Here, everything has even degree except for 2 of them, so that's fine. Here, everything's odd degree except for 2 evens. Here, everything even except for 2 odds, and that'll do. Yay. Oh, for which value of n does G not have a Hamiltonian circuit? Oh my goodness. Hamiltonian circuit? Oh, which values does it not have a Hamiltonian circuit? Oh. Well, 3. Oh, there was a theorem in the notes that says when you've got, remember there was a theorem that says when you've got enough edges, you're always going to have a Hamiltonian circuit. So, I think everything else will be fine. Yeah, I think everything else is fine, just that one. Oh, no, okay. Let me just draw.
Can you watch Odd Squad?
Yes, you can watch Odd Squad. Okay. Yep. Huh. Oh, does G have a Hamiltonian? Oh, I've got it read it backwards. Okay. Yeah, everything except 3. Okay. Thank you, chat. My brain has left me. Yep. Yep. Oh. For which values of n is it planar? Alright, well, 3, that'll be planar. That's just a 2-path. K4 will be planar. K5 with one edge removed will be planar. And everything else is going to contain K5. So they won't be planar. Yeah. So remember that the only way to being if you contain K5, then you're as a subgraph or anything homeomorphic to K5, then it's non-planar. Now K6 with one edge removed is going to contain K5, as will K7, K8, K9, and K10. They're all going to contain K5. K5 with one edge removed will not contain K5, so it'll be fine. You can have everything up to K5. Piper believes the two graphs below are isomorphic, but is not sure how to prove this fact. Show the graphs are isomorphic by providing the isomorphism between them. Cool. Well, let's see. There's one edge of degree 3 here, so I know those are going to be the same. So B is the same as U. No, wait. Yeah, that's fine. They're the edges of degree. B is the same as C. C is the same as U, the two edges of degree 3. No, C's got degree 4. Ugh. I need to eat. B is the same as U. There is only two edges of degree 3. The two neighbors of the edge of degree 4, the vertex of degree 4. Yeah. F can be X. E can be Z. And then there's just the neighbor of B, which is D. That's the vertex of degree 3. And that can be V. And there's a vertex of degree 2 in here, that's A, and that has to be equal to W, the other vertex of degree 2. So I think that one's it. Yay! Okay. My brain has officially stopped working, so I might leave it at that for the stream. I will get back and I'll post on Moodle about that that other question that look, I can't even count right now, so I'm not going to tackle the hard question. I'll just post something on Moodle about it. Other than that, that's pretty much the format of the exam you can expect. Are there any final questions? I'll give you guys a moment to respond. Yeah, okay, cool. Thanks everybody. Good luck in your tests. I'll still be monitoring the forum on Moodle, so feel free to post questions and stuff in there. Will our final level of difficulty be the same as this exam? It will be similar. There will be loads of easy questions, there will be some more difficult questions. You need difficult questions in an exam simply to so we can distinguish people from HDs, from Ds, from credits and that kind of stuff. So you can expect some of the questions to be more difficult, but you can also expect the majority of the questions will be possible for you with a bit of effort. So don't get put off because there was a hard question in the exam. That's only there for the people who, really shooting for that like super HD. Because we need to put in a question like that, otherwise it's not fair. Otherwise, yeah. So in our final, if we have the correct answer with the wrong expression, we lose mark. No. If you have the correct answer, you get the mark. Something's gone wrong there, and I need to investigate what it is. Yeah, I'll investigate that and get back to you. your correct answer gets the mark, and it shouldn't matter what the formatting is. Alright, I think I'm going to end the stream there and rescue my daughter from iPad time. So thanks everybody, and I will catch you all later.